Okay, I posed the following hypothetical situation. You've noticed that golfers, professional golfers, make a lot of money, so you decide, well, I better take up the game and get really good at it so I can make a lot of money too. Well, that's pretty unrealistic because if you don't start pretty young, you're almost impossible to get to the level of skill of the people that make good money playing golf. However, we don't know that. So we go ahead and we decide, okay, well, I'm going to learn the easy part of the game first. I'm going to learn to putt. Well, actually, I'm a fairly experienced golfer personally, and I can vouch for the fact that putting is not the easiest part of the game. But it's probably the part that a novice can do better relative to the rest of the game till he or she learns to swing a club properly. So anyhow, you're going to start putting, and that's enough about the situation. So you're putting, and you're putting at a linear scale with a target at 0 centimeters. And what do I mean by that? It's, and I don't have one up here, but you got a stick, and you got 0 marked here, and then you mark it off in centimeters, 1, 2, 3, 4, 5, 6, and then to the left, -1, -2, -3, and so forth. So we get, 6 feet away and we start putting the ball, trying to hit the 0. Now, everybody is going to have some tendency, and this is kind of extraneous material, but this is kind of important to know. Everybody is going to have a tendency either to putt to the right or the left. Okay? And that's kind of an inherent neuromuscular tendency that you don't have any control over, and very hard to compensate for it. Okay? And that's true in scientific observations. People that use telescopes to plot the positions of stars. Everybody had certain inherent biases in the way they observed the information. Now, it was real important to observe the stars accurately, but there are limits to how accurately people could do it. So the astrologers had a terrible time, and astronomers did as well. Okay, but they knew what their limits of tolerance were. So let's just say that you find that your mean is plus 1.4 centimeters, meaning that you tend to hit that target on the average 1.4 centimeters to the right, about that far to the right of the center. Now that's pretty good if you're only off by that much, but that's the way it goes, okay? So let's just assume that's the case. And let's also say that you have a standard deviation of 3 centimeters in where you hit the target. And you've putted the ball so far 1,248 times. Now, how many then, once you have this information, how many of these trials do you expect would fall between plus 2 centimeters and plus 6 centimeters? How do we analyze that situation? Well, we have a mean and a standard deviation. So we're going to kind of assume that this phenomenon is normally distributed. It's usually a good first assumption. Sometimes it doesn't hold up, but very often it does. So we draw our z-axis with our mean at 0 and our standard deviation, 1 standard deviation to the right and 2 standard deviations to the left. Okay? Now we could draw the normal curve, and we will because you see them drawn here, but right now we just want to get the z-scale, and we want to compare it with the x-scale, where x stands for each putt has an x, okay? X is the position at which a putt lands. The mean value of where the putt, I said lands, but where it hits the target, where a putt hits the target is 1.4. And this is in centimeters, and it would probably be a good idea if I had a piece of white chalk to indicate that on my scale. I don't have to write centimeters after every one of these, it clutters things up. but I do need to know what my scale is, so this is a good way to specify it. Okay, so the mean is 1.4 centimeters. Okay, that corresponds to z equals 0, because that's where the middle of the distribution is going to be. Okay, then the standard deviation is 3 centimeters. So 3 centimeters from the 1.4 to the right, we get 4.4. That's one standard deviation to the right. So 4.4 centimeters plus 4.4 centimeters is going to correspond to z equals 1. One standard deviation to the right of the mean. Okay, another standard deviation takes us to 7.4. Standard deviation, remember, is 3 centimeters. So if we go 3 centimeters from 4.4 centimeters, we end up at 7.4 centimeters. And that corresponds to z equals 2. Going the other way, if we go 3 centimeters in the opposite direction from 1.4 centimeters, we end up at negative 1.6 centimeters, and that corresponds to z equals negative 1. And then 3 centimeters to the left of that is negative 4.6 centimeters, and that corresponds to z equals 2. So here is an axis labeled with z and labeled with x. And we want to determine how many of our results are between plus 2 centimeters and 6 centimeters. Now, where is plus 2 centimeters? Well, plus 2 centimeters is going to be between 1.4 and 4.4, and much closer to 1.4. So I'm going to say z equals 2 centimeters is about here. This is going to indicate, I'm sorry, not z equals 2. This is going to indicate x equals 2 centimeters. And 6 centimeters, well, it's between 4.4 and 7.4, somewhat closer to 7.4 than it is to 4.4, so I drew it here and said, okay, that's going to be x equals 6. So we've labeled our x and z axis, and we've labeled the two positions between which we want to determine the number of hits that we would expect if our distribution really is normal. Okay, well, I'm going to stop there and we'll pick up again. And what we need to do, and what we're going to do, is we're going to figure out what the z value is for x equals 2 and what the z value is for x equals 6, so that we can then apply the z table in a sensible manner to this situation. Okay, so we have to figure out the z for x equals 2. Now we can see from the picture that it's going to be a good bit closer to 1 than it is to 4.4. Where I've got it drawn there, it looks like, probably about 0.2. We'll see if that works out. And where I've drawn the x equals 6, and remember that's just where I drew it, that's not where it probably really is, I would say that that's probably at 4.6 or 1.6 or 1.7. It's between 1 and 2, closer to 2 than it is to 1. It looks like 4.6 or 4.7, 1.6 or 1.7. If this is 1 and this is 2, then 1.5 is here, so that's somewhat to the right of 1.5. Is it far enough to be at 1.7, or do we have to say it's at 1.6? Well, we're going to calculate it and see what it really is.